Hello everyone. My name is Pengcheng Wang, from Tomorrow Advancing Life Education Group. Today I will talk about our work on the 2020 EmotioNet Challenge. Here are our team members. Both of them contribute greatly to this work. This page is some results in our report paper, and both of these are computed on the dataset B. The dataset B is randomly chosen from the optimization dataset. Our model is get a final score of 18.3 first, and after we assemble several models with different backbone, we get nearly 9.44 higher scores. And with multi-crop testing, pre-trained models and fine-tune, choose best model for each AU, and different threshold strategies, we get a much higher final score finally. And then I'll show you some solutions of our work. I will present our work following the below solution. The first is about the multi-view features and losses we used. And then I will show you the different strategies for the emotion and head pose problem. About the emotion and head pose problem, I will explain later. And the third is about batch balancing for positive and negative samples. The fourth is the noise dataset processed method, and we pre-trained a model on the filtered dataset. And a classic computer vision method, multi-crop testing. And then is the model chosen and the threshold strategies. The last is ensemble model. We used a multi-view feature extractor as our baseline. That was proposed by Xiao Liu in his paper named Multi-Label Semi-Supervised Facial Action Unit Recognition. The network is almost like this. For an image, we used two models to extract features F1 and F2, and then the two features are input into two multi-label classifiers to predict each AU's probabilities. The main idea is from co-training method. It to force the two classifiers to capture different view of AU features and predict consistent labels. Just like mentioned in view 1 and view 2. The view 1 thinks the feature is the lips of him is apart, and the view 2 thinks the feature is the texture of his mouth is like smile. Although they are different, but they predict the same label. To do that, Liu was make a constraint on the classifiers using the loss MV and the loss CR. Specifically, the loss MV is making the classifiers weight synchronizing to get independent features, and the loss CR is to force the classifier of different views to get consistent prediction. But Liu was used that for semi-supervised learning. Actually, we used these two losses as a regular instance for supervised learning in our work. The EmotioNet dataset contains 23 action units. The first 17 action units are found is about emotion problem around the face area. And then the last 6 action units are about head pose problem. Well, we process and train these two problems separately. About the first 17 action unit, we first use a face detector to detect face box and fill landmarks to crop face. By using random downsampling, occlusion, the flip to augment the date. After doing that, we resize the face to a fixed size, with keeping the face origin ratio, and lastly align the face. Well, unlike the first 17 action units, the head pose problem needs more content of image, so we expand the face length of 1.5 times. Mm. A simple size strategy without random flip and align, because the flip will offset the AU, the last 6 AU label, and align is improper for head pose. We summarize the positive and negative samples of the optimization dataset and find the positive samples is much less than the negative samples in some AU. We used a simple batch balancing strategy like the middle picture shows. When the blue instance is positive and the white instance is negative, the green upward pointing arrows indicate the backpropagation error. If there are much less positive samples in a batch of AU or some AU that's like AU1, we will random mask some negative samples to prevent backpropagate in order to keep the ratio of positive and negative samples. Well, the condition is whether the bit is larger than the number of positive samples. If the condition is true, we will do that method. We will do that process. If the condition is false, the process is just normal. Well, for example, if we have 100 AO1 samples in a batch, 10 are positive and 90 are negative, and the bit is 0.2 multiply 90 equal to 18 is larger than 10. So we random choose 18 negative samples to backpropagate. And by the way, the hyperparameter alpha is an empirical bit. We have tried a lot of other numbers, like 0.1 or 0.5. Well, around all these alpha, 0.2 is the best, so we just define alpha is 0.2. We can get nearly 900,000 noise excites, which are labeled by machine, and 25,000 samples precisely labeled by experts. We divided the precise labeled dataset into dataset A for training and dataset B for testing. And it is improper to use the noise dataset training directly. So we filter it using our baseline model with some strategies, just like the label must be consistent with our prediction with higher probability. Through doing that, we get the dataset C. And by mixing the dataset C and dataset A, we pre-trained the model and fine-tuned on the precisely labeled dataset A. By doing this method and strategies, we get a more generalized model. The next is a classic computer vision method, multi-crop testing. We choose 5-crop testing, contains top left, top right, center, bottom left, bottom right to inference, and finally average the logic to get the prediction. During the training process, we found an interesting phenomenon that different AU have a different convergence speed. As our training process is a multi-label problem, which could be treated as a special multitask problem, different tasks may have different convergence speed. Like the picture below shows, the black star is the highest score of that line, and we can see that with the training process going, some AU may have been overfitted, like AU1 and AU9, where others still underfitted, like AU5 and AU15. So if we just choose the highest score of the average line, we won't get the best performance of each AU. We maybe just get the medium performance. And by the same logic, the threshold of final sigmoid logic of each AU to judging the final prediction being 0 or 1 could be different too. So we choose the best model for each AU and different threshold for each AU too. Here are some backbone models we used, contain the EmotioNet family and ResNet family. We have trained several models to finally using a linear regression model to resemble these models. And here are our results of the challenge, contains the validation phase and the testing phase. Well, thanks for your listening. And if you have some questions, please do not hesitate to ask. I'll try best to answer.